Hello, everyone, and welcome to the Weekly Space Hangout for Wednesday, October 18th, 2017. I'm Fraser Kane, publisher of Universe Today. This week, we've, of course, got the big news, which we'll get to in a second. Plans to put an inflatable habitat in lunar orbit. Intense yearly rainstorms on Titan, and peering to the far side of the Milky Way. Joining me this week, our regular full complement of co-hosts, Morgan Rembrick. Morgan.
Hey, Fraser. Sometime I'm going to write something very bizarre in the little show description and see if you just read it verbatim out into the world.
I would. Don't even do that.
Don't go there.
Yeah, I will totally do that. Why would you do that?
Halloween.
Kimberly. You're here, Kimberly.
Hi, Fraser.
How's
Hi,
it going?
Fraser. Hey, hello, everyone. Happy Wednesday. Halloween episode. I'm going to put something super fun in the description. It'll be great.
And I will read it out like a robot.
Yes.
And Paul Matt Sutter.
That's me.
Paul
I
M.
won't try to
Sutter. Paul M.
Paul
Sutter.
M.
Doctor
M stands for
Paul
that.
M. Sutter. Yeah.
Yeah. The doctor stands for doctor. And, I won't try to trick you. I'll just play it straight. Straight shooter.
No.
Nice guy, Paul.
I deserve it.
Skip to Paul.
All right. Well, let's get on, obviously, with the big story of the week, and that is, of course, man, I have never seen so many press releases that said the same thing over and over and over again. Paul.
What's going on? It's like there's as many press releases as detections and observations.
Yeah, Paul,
We've created our own gravitational wave.
Give us the lowdown, Paul. What happened?
Yeah, so LIGO noticed something funny going on, and as a signal came in, and they recognized the signal as not to merging black holes, but to merging neutron stars. This was a much weaker signal, transmitted over a much longer period of time. Typically, a black hole merger just takes a couple seconds. This was extending up into the tens of seconds, up into a minute. So they figured this might be a neutron star merger. This signal, by the way, was detected last August. And they sent out immediately a worldwide alert. So LIGO has this fantastic network of over 300 scientists and institutions and collaborations on speed dial. It's all automated. As soon as the software triggers on a suspected event, the two LIGO detectors and the Virgo detector work together to pinpoint its location on the sky as best they can and send those coordinates out to everybody in the world. Say, hey, are you seeing what we're seeing? And it just so happened that Fermi and Integral, two gamma ray instruments, were looking in roughly the right patch of the sky at that time, and were taking data and were observing, and they saw a very bright gamma ray flash. So they sent out the word, say, hey, we saw gamma ray flashes, and then other observatories all around the world and in space started tuning their instruments to the same patch of sky. And what we saw was an event in gravitational waves, in gamma rays, in X-rays, infrared, visible, microwave, radio, the whole deal over the course of 2 or 3 weeks. I think this signal was still detectable. And what it turns out to be is, we suspect, and we're pretty sure about this, is the collision of two neutron stars. Two massive cores left over from dead stars spiraling in towards each other. We caught their final moments of last embrace. That collision generated a gigantic explosion, which we were able to see. And there's much more to talk about related to this, but we should probably bring in the whole panel.
Oh, don't worry. The panel will jump in whenever they need to.
I could hear them. I could hear Morgan panting, getting so excited about this.
So one of the things, Morgan is clearly excited. But one of the big things, of course, was this idea of, that it was the Killa Nova. And I've got to be honest, I had never heard that term before.
Yeah, is that a real term?
Did they just make this up?
I think it's I've seen the term floated around because we suspected, well, what this discovery also opens up is we've been discovering what are called gamma ray bursts for about 3 decades now. These very brief, very intense, very localized sources of gamma ray radiation. And some people suspected it might be because of neutron star mergers. That was one of the leading candidates. And there was a nickname for that because these are so powerful. It's more powerful than a nova, more powerful than a supernova. I guess we're just skipping hypernova and going
Or
right
meganova.
or meganova. I think isn't that Transformer? I'm not exactly sure. And then going right to Killa Nova as kind of an informal nickname for neutron star mergers.
What I thought was so cool about this event is that it confirmed these really basic things that I just assumed we already knew. Like, for example, the fact that gravitational waves travel at the speed of light. That's something that, the theorists had said, yeah, that makes sense. But we had never seen it before because we'd never seen light associated with a gravitational wave. But the fact that the wave washed over us and the light appeared at the same time tells us, yes, gravitational waves travel at that fundamental speed limit. And that's just such a basic thing that we've been talking about gravitational waves now for years, and we didn't know for sure had to be true.
But there was pretty indirect evidence at this point, right? That we knew.
Oh, absolutely. There's no reason to think it wasn't the case. But just, that was one of the bullet points in the press release. And I thought, wow, that's just a really basic thing that this detection let us figure out.
My favorite part of it was that they also detected the synthesis of gold and platinum and all these heavy elements that don't form in the cores of stars, and they shouldn't be in neutron stars, and they really only happen in these gigantic explosions, kilonovas and supernova. And they detected essentially the entire history of the periodic table in this one event.
Well, Paul, I'd understood that gold, I've always been telling people that gold had been formed in supernova, all the heavier elements. I even think Carl Sagan at some point told us this. And if I understand,
Carl Sagan's not around anymore.
But if I understand correctly here, there was a problem with the physics of it coming from super. Can you explain a little bit about that and why researchers were thinking it was neutron stars and not supernova?
Yeah, so when you look at the upper end of the periodic table, when you get up into gold and platinum and then even heavier stuff, and you start looking at the detailed nuclear physics of what it takes to synthesize those elements, there are a couple processes that kind of shake out that allow you to build elements in that upper end of the periodic table. One is called the R process and the other is called the S process. R is for rapid neutron capture and S is for slow neutron capture. And there has been considerable debate, and there still is a lot of debate, of what process, this R process or this S process, dominates the production of heavy elements, and then where can you generate these processes? Where can you get fast-moving neutrons that are going to slam into atomic nuclei and cause them to transmute into higher elements? And where you can get slow capture, where you get a different family of elements from that process. So it's definitely that supernova do generate a bunch of the higher elements. It could be that most of the higher elements are only going to be found in the so-called Killa Nova because that's where you get the energetics, the right conditions for this rapid neutron process where you can generate the higher elements, where it could be the supernova, just the physical mechanisms happening in those shock waves. We're going to give you the right set of conditions for the fast neutron capture process to generate those elements. There still could be channels for making the higher elements in supernova. So it's not like supernova are not generating the more massive elements, but now we know for sure a lot of them are going to be formed in these neutron star processes.
And I think the other part is just how was anyone expecting to detect a neutron star with the configuration that they had with LIGO and Virgo? Like, it was because it happened so close, right? Like, that's why they got it.
Like 130 million light years away. Yeah. So it's the closest, the brightest gamma ray source we've ever seen. I'm not 100% sure on that statement, but something like that. So this was very, very close, very, very bright. And just in time, we had all three of our gravitational wave detectors online. If we only had two of them, if this happened a year ago, where we only had the two LIGO detectors, we would not be able to pinpoint it so well, and we wouldn't have gotten this rapid response within the hour and within the day of follow-up observations, and we'd still be relatively in the dark.
It's so exciting how rapidly we're getting results from these programs now that they're operational. LIGO's only been working for like a year or two, and Virgo just for a few months. And we turn these things on, and bam, immediately a major discovery. And that tells us that we're going to keep finding these things. And, in a couple of years, we're going to stop reporting on them in the same way we stopped talking about individual exoplanets, because it'll be old news. And that's a really exciting place to be.
I think at design, peak design efficiency, LIGO and Virgo are expecting on the order of 10 neutron star mergers per year.
Wow.
Oh, really? See, based on how close this was, I was sort of expecting this to be a fluke. This was like a Supernova 1987A, and that you're not going to see something this close with this kind of energy for a long time. It'll be a while before they'd be able to sort of confirm this and find more of them, until they build more sensitive instruments to be able to find them at different distances and at different masses and things like that.
Yeah, that's exactly right. We didn't expect to see neutron star mergers so quickly, because we hadn't brought advanced LIGO and advanced Virgo down to the sensitivity thresholds that we thought we needed to detect neutron stars. So this is the exact same story with the original black hole merger detection of 2 years ago. They just turned on advanced LIGO. They thought it'd be another half decade of fine tuning before they'd nab that first black hole merger. But it turns out the universe is louder than we thought. And as soon as we were able to dip our toes into the sensitivity regime, we're just able to start getting signals.
There's some really interesting things about this detection. One is that the stars that formed them probably formed, I think, 11 to 12 billion years ago, and have been spinning around one another for this entire time, and they inching closer and closer and closer. One question that I had was, like, what causes them to move closer and closer to each other over that 12 billion years?
Yeah, it is the emission of gravitational waves. It's very, very weak. It's very, very small when the stars are very far apart, but it is enough to sap energy out of the system, to sap angular momentum out of the system, and allow the stars to slowly in-spiral. And as they get closer, their disturbance, their effect on space-time grows stronger. The emission of gravitational waves grows stronger. And so that increases the rate of in-spiraling and merger until you get this catastrophic collision.
Yeah. And then, of course, the other thing, and people mentioning this in the chat, is that the actual explosion was off axis. So it wasn't one of its, it wasn't pointed at us. It
wasn't at us, yeah.
And, because the folks at LIGO had said, oh, the explosion is in the constellation of Hercules. It's in this kind of, I forget what it was, like 100, like a 30 by 30 moon area. And to look inside, and everyone looked around for it, and they found this faint little teeny brightening in this one galaxy. Would anyone have noticed this if they hadn't been looking with that many telescopes with that level of care? Because it was there and it was gone within days.
I think Fermi and Integral and the other gamma ray telescopes were operating in this general area. I'm not 100% sure. So I'm sure it would have been noticed and cataloged somewhere without much comment or interest.
Right. Okay. Yeah. No. That Fermi did, if I recall now, Fermi did detect it. And so they had a separate, like NASA had a separate observation from Fermi of a gamma ray, but they would have just put that back onto another short gamma ray burst.
There's another one added to the pile.
Yeah, those are mysteries. Don't know what those are. One other thing, Kimberly was saying some of the stuff that got confirmed. One of the things that got confirmed, or this can be used for, if I understand, is to literally measure the expansion rate and stuff of the universe.
Yeah.
Well, ESO said that.
Okay, ESO, bring it on.
That's a skeptical noise.
Kimberly, why don't you talk more about that?
No,
Me? No, I want you to talk
It was
about
your idea.
no.
Who said it was my idea? Fraser said it was my idea.
Yeah.
I didn't say that was my idea.
Yeah, no. It was ESO's idea. Remember?
ESO said it was ESO's idea, not me.
Yeah, I
If
can
you
I can
don't,
read you the ESO press release if you need.
Okay,
While you start showboating, I will grab ESO's statement.
Well, here's the thing. If all neutron star mergers happen with a very, very similar process, if it's similar mass objects with similar time scales for in-spiraling merging and then ringing spacetime, that is a quote unquote standard candle. Because if you know the distance, you can use this to measure a distance to that particular galaxy. Once you have a fixed distance, you can measure its redshift by other means, and then you can construct a distance to redshift relationship, which lets you measure the expansion history of the universe. So this is, go ahead, Fraser.
Oh, I was just going to say that one of the questions that you don't know with these things, when you're trying to develop a standard candles, you don't know how much energy was released in the event. You don't know the masses of the things involved. But the gravitational wave told us that the masses, like one was 10% more massive than the sun, the other was 60% more massive than the sun. They knew exactly how much mass was involved in the collision. Therefore, you don't just, if I understand, you don't just have it's not like it's a white dwarf where it's always 1.4 times the mass of the sun. You literally can measure with high precision the mass of the things involved, do your calculations to figure out the amount of energy that's released, use that to calculate the brightness, and that'll tell you how far away it is, and then look for these objects around the universe. And I guess that's what they're getting at, is that you've never had a method that gave you the mass of the ingredients of the explosion with that level of precision. Now suddenly you do. And now suddenly the whole universe, as you look around, you go like, oh, now I know the mass. Eventually they will know the mass of all kinds of crazy interactions at all kinds of distances, and be able to then start track dark energy and figure out what's happening with the expansion of space-time. So,
right, unless your estimation of the mass has some dependence on the distance. I'm not familiar enough with the detailed calculations of these distortions in space-time that LIGO picks up and how they reconstruct the masses. If it's totally independent of distance, then you don't know the distance to the object, and you would have to measure it by other means, in which case you gain nothing. If it does depend on the distance, and then you have to do a joint constraint of both the distance and the mass, you can use that as a standard Siren, I guess is what they're calling them now. And you could construct this redshift distance relationship like we do with supernova, like we do with baryon acoustic oscillations, like we do with so many other things. It's definitely possible. It's definitely viable, potentially viable. It's definitely interesting and worth pursuing. If you're only going to collect 10 of these per year, you will, even if those are 10 high precision measurements, you're probably not going to beat down your systematic uncertainty enough and build up enough statistics that you can actually build a full-scale Hubble diagram. Maybe this will, I'm thinking out loud here, maybe this will help anchor the low end, the nearby universe end, which we're having some difficulty with, because right now we only have supernova, and supernova are presenting their own challenges. There could be utility here. Sure.
So
a ringing endorsement from Paul Sutter.
Gravitational wave.
How long were you thinking of that pun?
He was panting the whole time. No, it is potentially very interesting, but it requires a lot more work than you might suspect.
Yeah, well, that's why I get to be just
Ain't that
a
always the
journalist,
truth?
as opposed to somebody who has to actually do the math. So, I mean, what next? I mean, there was 4,500 separate researchers with their names
Another
on the
Nobel
paper.
Prize, I guess.
Do you think this is a Nobel Prize?
No.
Not again.
Not again.
They just handed one out for
They
gravitational
they
waves.
should have waited a year,
I'm already.
and then they could have added this to the citation list and called it a day.
And what's immediately next, I think, is nothing, because a lot like the Large Hadron Collider in Switzerland, these big detectors are constantly in need of maintenance, and I think they've already shut down again for like a year to do upgrades, to do maintenance. And so for a while, at least, we're going to be in this situation where we turn these guys on for a little while. The universe pours in, we make a few detections, and then we got to turn it off, power it down, do a bunch of work, increase its sensitivity, and we're just going to sort of step our way up the sensitivity ladder year by year in this sort of on again, off again approach.
I think I heard during the press release that Virgo was experiencing a lot more noise than normal, but because this event lasted so long, they were eventually able to pick up on it, and they were able to triangulate the position.
100 seconds.
Yeah, if it was short, if it was a black hole merger, Virgo would have just totally missed it because it would have been lost in their noise.
So there you go.
I hope they get that figured out.
Yeah, they're working on it. They've only been working on it for 3 decades.
The one question came from Quadlibet, which is not actually related to this, but the gist being that big supernova can be so powerful that they don't even leave a black hole behind. Can someone explain this without damaging my brain? So this is a type of supernova where the star is so big it just goes, and then that's it.
A Killa Nova, if you will.
Yeah, but it's not a Killa Nova. It's like what, like a type 2
half Killa Nova.
half Killa Nova? No gold gets formed. Just
I guess the super short version is the interior of a star, as it's blowing up, is an incredibly complicated place with many competing forces happening at once. If gravity wins in the core at the end, you get a neutron star or a black hole. If other forces win in the end, you don't.
These are the pair instability supernova, is that right?
Pair instability supernova, even this neutron star merger, we're pretty sure it ended in a black hole, but it could have ended up in a new neutron star. It just depends on the detailed physics.
Right.
We don't fully, even regular supernova, getting all excited here, moving my arm around. Even regular supernova, we're not 100% sure of the physics that's going on. We can't recapture, we can't capture a supernova explosion in, say, simulation.
And then there's a whole other kind where they just fail. They don't even go kaboom. They just collapse in on a black hole and they're just gone.
Yes.
Doink.
Which is amazing too. So
All of our favorite fail modes.
So I think that's really interesting. So now we're going down a new rabbit hole, but I hope people are entertained. But which is just this idea that you don't understand really with a high level of precision what is going on inside this supernova. And some of the most biggest, powerful computers in the world are used to try and simulate this.
Physics are too complicated right now. But guess what's going to help?
LIGO?
LIGO.
Please say.
Exactly. That's actually the next thing on the checklist. Number 1 is black hole mergers. Number 2 is neutron star mergers. Number 3 are supernova. Gravitational wave signatures from supernova give us a window to the interior of the explosion in a very similar way and complementary way as neutrinos do, where we can finally get some more understanding of what the inside of a star is doing as it's dying and blowing up, which can help constrain our models, which can help inform the simulation so we can figure out what are the detailed physical processes.
Right on. All right, before we move on to the next story, I just want to remind everybody that we couldn't do this show without the assistance and support of the Weekly Space Hangout crew. This is, of course, they're the fans, they're the producers, the executive producers. They're the people who we work with every week to bring you the stories, to bring you the guests, and to bring you the chat that's going on during the live show. So if you want to be a part of this community, just go to wshcrew.space. They will give you lots of information, show you the Slack channel that you can come and join us and talk about what's going on with the Weekly Space Hangout. Totally free, just a great community of super space fans. All right, well, let's move on to the next story. I choose
Pikachu.
Kimberly, I'd like to talk about peering to the
Yeah.
far side of the Milky Way.
So, in the same realm of finding distances to things we didn't think we'd ever have a distance to, astronomers were able to use the Very Long Baseline Array, which is a very long baseline radio telescope array that spans the entirety of the continental U.S. and the Caribbean as well, to measure the distance to a star-forming region that is 66,000 light years away. That is more than twice the distance from the sun to the galactic center, and it's actually all the way past the galactic center, clear on the other side of the galaxy, nearly to the edge of the far side of the Milky Way galaxy. It is by far the farthest object within the Milky Way galaxy that we've been able to get an accurate distance to. And the reason we were able to get such an accurate distance to this very distant star-forming region is using the exact same process that we've used for hundreds of years to get the distances to nearby stars, and that is parallax. But
they parallaxed this sucker?
They parallaxed this sucker.
Wow. That's actually really impressive.
Over a 6 month measurement. So if you don't know how parallax works, is when the Earth moves from one side of the sun to the other over a 6 month period, we get slightly different angles of perspective on everything in the sky. And if you get a precise enough measurement of how each object shifts back and forth, you can use basic trigonometric functions to get an accurate distance, just based on how far things have shifted over a 6 month period.
Put your finger in front of your face and wink.
Yes.
I've
Exactly.
never seen a press release that doesn't say that.
Yep.
It's true. Yes.
I'm doing it right now.
Extend your arm, put your finger in front of your eyes, close one eye and then the other. You see your finger shift back and forth, and we're all doing it on the screen right now.
I'm pretty sure my finger is in front of my
And you see your finger shift back and forth. That's parallax. And that's what the astronomers were able to do using a very large radio telescope to accurately measure the distance to a star-forming region 66,000 light years away.
That's crazy.
Is this through the core? Is this through Sagittarius?
Is it in the zone of avoidance?
I'm not exactly sure if it's through the zone of avoidance, but it is through the center region of the galaxy. And that's not quite through the exact center. It's a little bit off center. But
so did they have to use radio because it's so thick and dusty?
Yeah, so when you're looking through the disk of the Milky Way, you have to go through all this dust and gas and all the stuff that gets in the way of just about any other wavelength aside from radio. And even with radio telescopes, it's really difficult to see through all this gunk. But they were able to measure the distance to this object because it is not only a star-forming region, but it has a special property. It's also what's called a maser, which is where molecules like water and methanol interact with radio waves in such a way that it amplifies the signals from the radio waves, making them much brighter than they would otherwise be, so we can see them from farther away. And there are hundreds of these masers in the Milky Way, and radio telescopes have whole catalogs of them to calibrate their instruments. And so because this star-forming region was also a maser, it was amplifying the radio signals. We could see it from so far away. And what I think is super cool, which I haven't mentioned yet, is that because we're essentially able to see all the way to the far edge of the galaxy, if we could use similar measurements and similar techniques to get distances to other masers elsewhere in the Milky Way disk, you could actually start to map out the structure of the Milky Way disk, which we still don't have a great idea. You have theories. Any picture you've seen of the Milky Way is really just what
Andromeda butt
is the best idea of what our spiral galaxy like us.
How the heck do you get a solid, accurate parallax measure of an extended object?
Because that's getting
it's not really extended. They said in the press release that it was the size of a baseball on the moon. So it's for all practical purposes, it's not that extended.
I see. So if it were closer, we would not be able to get to a parallax because it would be so extended.
Right. If it was something like even probably Hubble's Pillars of Creation, that's too big to get a good parallax for, because every little point on this extended source would be a slightly different distance away.
How ironic.
So, yeah. But it's super
The
cool.
closer it is, the harder it is to measure its distance.
So how did we end up in a situation, and this is a rhetorical question more than an actual one, in which the first time we measure something this far away, we have to look straight through the galaxy to do it? You'd think that we would have seen something like this sort of off center a little bit before making this really challenging measurement of going right through the gut.
Well, but if you're going to go for the longest measurement you can do, you're going to need to go right through the heart of the Milky Way to the other side. You can make shorter measurements, ones that are off to the side of where you are, but to make the one that's going to give you the longest possible measurement, it's got to go straight through. And the only wavelengths that can do that are radio and infrared, right? To actually get through the dust and gas at the middle of the Milky Way.
Yeah, and so this measurement was part of a project whose sole goal is to actually create a map of the Milky Way disk, is to get accurate distances to what seem like point sources, or, try and actually pin down distances to individual objects and map out the structure of the Milky Way. This is the whole purpose of this large project. And if I were in charge of this project, I would go for that farthest object to show that I can do it, that the lofty goal of mapping the Milky Way point by point, piece by piece, is possible by going and showing I can do that farthest side of the galaxy.
So
if I were me.
Your future research is funded.
Yes. But that's the cynical way to think of it.
Right.
And I'm not cynical this second.
No, of course not. Morgan, let's hear about Titan. I believe it's Titan.
Now that Cassini's ended, we're firmly in the phase of planetary science where we've made a bunch of observations. It's time to turn around and do a bunch of simulations. And we'll do simulations for 10 or 15 or 20 years, and then it'll be time to have another mission to disprove all of those simulations. And what we're talking about this week is rain on Titan. Probably the most important thing that Cassini contributed to our understanding of the solar system is Titan as a world. It's not a sort of a barren, desolate moon like our moon or like Jupiter's moon. It's kind of a living, breathing world with liquid on its surface, a thick atmosphere, storms that seem to roll through. And what this set of simulations was looking at was the rain that those storms might bring. And we had thought in the past that big rainstorms on the surface of Titan might be sort of like a once in a millennium kind of event. But these new simulations suggest that they're a lot more common than that, more like once every Titan year, which is about once every 30 Earth years. And when we say, a big rainstorm, we're talking about the kinds of torrential downpours that we've been seeing from the hurricanes here on Earth, something like 30 centimeters a day of rain. But of course, this rain isn't liquid water. It's liquid methane, which is the working liquid on Titan. And it's happening in a different place than we'd expect to see them on Earth. It's happening in the wet part of Titan. But instead of the wet part being around the equator, the wet part on Titan is actually near the poles, sort of in the 50 to 80 degree latitude, both north and south. This is where we find most of the lakes and oceans on Titan, and this is where the simulation suggests, unsurprisingly, we see the most rain. And what this paper did that was really great was they pointed out that their simulations are actually connected to things we can observe. Because one of the most interesting observations that Cassini made on the surface of Titan were these structures we see all over the Earth called alluvial fans. And you can kind of think of alluvial fans as like river deltas. They're places in which a stream kind of exits its channel and spreads out widely. And when liquid like water or methane is traveling quickly, it can carry a lot of stuff with it. It can pick up dirt and sediment from the bottom of the river and carry it along. But when that river suddenly spreads out, the velocity of the liquid slows down a lot. And then it can't carry as much stuff and it starts dropping it. And it makes these really distinctive fan-like structures that we use to figure out where ancient rivers flowed on Earth. We can see them from orbit, for example, on Mars, and see where rivers must have been flowing in the past on Mars. And we see these on the surface of Titan, clustered around the 60-degree latitude location. And that's the exact location that these models suggest the heaviest rains ought to be falling. And so in these 30 centimeter a day kind of downpours, it fills up these small channels on Titan. The water's rushing across. It picks up debris until it kind of bursts forth into a delta, and then it drops all that material. And we can see that many, many years later with radar images by Cassini.
I can't believe, I just can't imagine. I mean, I believe, obviously, but just imagine to be standing on the surface of Titan and have this downpour of liquid methane falling from the sky and pooling up around.
You probably don't want to be standing there.
Might die.
No, well,
it would be
with my coat on and my.
It'd be a really weird It'd be a really weird experience because the surface gravity on Titan is a lot lower than on Earth, and the pressure is even higher. The atmospheric pressure is even higher than Earth. So the rain would be like it's falling in slow motion. The drops would be coming down really slowly relative to what we're used to on Earth because there's not as much gravity to pull them down, and there's a lot more air for them to push against.
Wow.
Hey, Morgan, why is Titan wet at the poles?
That's a good question. And it's probably because of the temperature needed to sort of create this precipitation that would create it. So on Earth, the sort of best temperatures to create rain happen in the tropics, and the tropics happen around the equator. But, methane is its own liquid, and it has its own phase diagram that can look very different than the phase diagram for water. And that tells us that a different combination of pressure and temperature are going to yield the precipitation and then the persistence of liquid on the surface. And it must be that at the sort of polar regions of Titan, we have that right combination.
I feel like the more that we learn about Titan, the more we realize how similar it really is to Earth if you just substitute methane for water.
Yeah, if you just move one notch over.
There's rivers, there's dunes, there's rainfall, now there's hurricanes.
It's a way more Earth-like place than Mars has been for billions of years. And I think it's a really fascinating thing to think about from the perspective of what we expect exoplanets to look like. Because here's a world that by all sort of bulk measurements is nothing like Earth. But when you start getting there and drilling down to these individual observations, lightning, storms, rain, rivers, lakes, dunes, even though it's made up of totally different stuff, the processes work very similarly. And that ought to give us a lot of hope that when we're looking at exoplanets, it's not unreasonable to think that they too might be behaving similarly to Earth, even if they're made up of totally different stuff.
But isn't it kind of a twofer as well? Because it's also under the surface of Titan, you've also potentially got this liquid water oceans with a crust on top of it, and the same kind of phenomenon that you're seeing it in Enceladus and in Europa as well, right? So you've got that whole potential for searching for life as well.
Wait,
and we don't even understand.
What was that, Paul?
I did not know this about Titan.
We don't know for sure.
Oh, okay.
We don't know for sure, and we don't even know why Titan looks like it does at all. Its gravity is so low that it has to be just sort of gushing methane to space. And yet here we see a whole ecosystem of methane-based processes where no other moon in the solar system has anything even 1% as much of this. So why does Titan exist at all is a question that Cassini has really been unable to answer, and is one of the reasons that Titan is among the top choices for places to go in the solar system when we head back to the outer solar system. It's such an anomaly.
Do you think that any of the Cassini finale data might help us with that? Figuring out why Titan is?
Probably not, because Cassini's finale was mostly focused on the planet and its rings. Cassini's studies of Titan have been distributed really well throughout the mission, because Cassini had to pass Titan on every one of its 294 orbits, because they used its gravity to change orbits without having to use a lot of fuel. And so we've made a lot of really close-in measurements of Titan consistently along the way of the whole mission. And these last few orbits, which were really great for the rings and for understanding the planet, actually took us farther away from Titan than a lot of places, or a lot of times that we've been there over the course of the mission.
Well, that just means we have to go back.
Oh yeah, we have to go back.
Submarine. That's the answer.
Yep.
That's
Let's
just
go
one
back.
answer. No, submarine, airplane, sailboat, rover, drilling system,
Titan.
astronauts.
Let's not do hot air balloons.
Why not?
Well, if you fill them up with like oxygen and then
I wonder what would be a lifting gas on Titan in an atmosphere that is
Helium would still work.
Yeah.
I think it's more the fire part.
Well, just take don't take oxygen. That's all.
you only need it to breathe.
Right. Just don't.
We have this conversation almost every show.
Do we about the things that we need to breathe?
Oxygen. It's
How
always oxygen.
troubling oxygen really is.
What
It's corrosive. It's oxidizing.
All right, so I'll go on to my story here. Thanks, Morgan. So my story that I'm bringing to the table this week is that Bigelow Aerospace and United Launch Alliance just announced that they're going to be sending their own inflatable habitat to the moon for a lunar outpost. So I'm going to put up a picture here. The plan is to send a what's called is the Bigelow B330, which is a inflatable habitat that will have about 330 cubic meters of interior volume, which is about the third of the volume of the International Space Station. So, and that's in like one inflated thing. And up until this point, Bigelow has launched. They put 3 inflatable habitats into space. There was the Genesis 1 and Genesis 2, which were sort of test platforms. They had a bunch of cameras inside and out, and they put them up into space, and they're still there, expected to last a little while longer. And then they put what's called the Beam, the Bigelow... inflatable. I forget the acronym, but this has been attached to the International Space Station. It was launched on a Dragon capsule, bolted onto the space station. They inflated it, and the astronauts have been enjoying the the additional capacity. Well, they haven't been like living in it, but they've been doing tests to make sure that it's safe and that it's stable and that it's it's got good structural capacity, and that testing how much radiation is getting through it. And NASA's pretty happy with the Beam, and each year they keep extending the mission. And so right now it's definitely going to last until 2020, and then they're going to keep extending it year after year. So the plan is, and this is sort of this collaboration with Bigelow and United Launch Alliance, is to carry the 330 on a Vulcan rocket, which is this new kind of half reusable rocket that United Launch Alliance is working on. It's not like a fully reusable rocket like the BFR, which doesn't exist yet. It will sort of have these reusable rocket engines, which are the sort of the expensive part of the rocket, and the rocket will take off, they'll detach, float back down to Earth on parachutes, be recovered, attached to a new rocket. Then one of these will launch the module to orbit. Then 2 more will launch carrying the fuel. They will inflate the habitat, transfer the fuel between these 2 upper stages, and then one of them will carry the 330 out to a lunar orbit. And then from that point, it's ready for NASA to spend time in this new lunar habitat. At the same time that the Deep Space Gateway is under development, at the same time that that SpaceX is dropping the BFR down on the surface of the moon, at the same time that the Chinese are going to be setting foot back on the moon with their Chang'e thing. So it's a
I'm having a strange 1960s flashback.
well, it's
Yes.
Race to the
5.
moon.
It's a whole new race to the moon.
Again, because we're not interested in Mars anymore, I guess.
No, Mars is out. Mars is old news. We're no longer interested in Mars.
It's overrated anyway.
So,
Well, no.
Fraser, I have 2 questions. When and how much?
So 2022 is when they think they're going to put it into low Earth orbit and send it up to lunar orbit. So that's soon. And
Can you really put a price on bounce houses in space, Kimberly?
Yeah. I don't know. I don't know what the price is. I don't know what the price of a launch on a Vulcan is, because these I don't think have
They
gone up
probably
yet.
don't either.
Yeah, they don't either.
Probably a reason that number wasn't in the.
So it's like on the one hand, Bigelow has been, man, like the heart of that company. They have been plucking away for feels like decades now, building up both privately and making partnerships with NASA and other people to try and build these inflatable habitats. They are certain that this is the way the future of human space exploration is going to go, is these inflatable habitats. Their bigger version is called the 2200. And so it'll have 2,200 cubic meters of internal volume. It'll fit on a space launch system in one launch and just go boom and just get
Are these just like one single giant room, or can they build them such that you can inflate them into a whole little castle?
Well, they will inflate.
Space castle.
Yeah, they will inflate, and then they will set up. They'll outfit it and set up small areas inside of it and stuff. So the whole thing will inflate, and then they will be able to fix it up however they want.
So I want to ask this question that Benjamin Valamont put into the chat, which is, why don't they make the Deep Space Gateway out of these things?
Well, so this is a funny thing, right? Like, so the Deep Space Gateway is going to be like a tin can space station, just like the International Space Station, except much, much smaller. And there's only going to be 4 modules on the Deep Space Gateway, and it's going to have a fraction of the interior room that the International Space Station does. So it really does make sense to use these inflatable habitats. But the way NASA works is they're very careful, very methodical, and to use this new technology and to base their development on it is something that they haven't fully committed to. And yet Bigelow's like, well, then we're just going to launch them. We're going to prove to you that this is a good idea. They've also been considering they could use these things for the moon. Like this idea of
Do they have a
inflatable
business
habitat.
model in? Do they have a business model in mind, or are they really just trying to prove that they work so that big space agencies like NASA will buy them?
Well, it's both. I mean, I think that their business model is to sell these to the big space agencies, and if that doesn't work, they're going to sell space hotels, right? Like Bigelow is certain that the future of human beings in space is inside these inflatable habitats. And then the question is, who's going to pay for these things and who's going to buy them, and will they find customers? And so they've been working really hard to try and find applications for the use of these inflatable habitats. And so now it's a very strange thing to have this competing possibility that you've got. On the one hand, you've got the Deep Space Gateway coming together at enormous cost. I mean, 4 SLS launches, all of the modules, and then the Russians are going to contribute 3 modules, as we mentioned. The Canadians are going to build the solar sail, of course, and that's vital. And then you've got what Musk is doing, which is completely different, right? Just landing right on the moon, calling it a day. So
Musk over there.
there's Musk over there. Just,
Thing.
yeah, I mean, the joke that I keep saying is like, when the explorers from Earth, when that first NASA mission makes it to Mars, they'll make it and they'll have to land at the SpaceX hotel and spa, and then just go through some kind of therapy for all of the space madness that they had.
Space therapists.
Yeah, exactly. Because SpaceX will have been there for 20 years already with a vibrant city. So there you go. It's like,
Well,
Yeah.
here we are.
Moon hotels.
Moon hotels. We got habitats. 5 separate plans to go to the moon.
Do these
NASA.
inflatable habitats make sense for surface habitats, like on the moon?
Absolutely. Yeah. I mean, this is one of the other developments that Bigelow has suggested they could use this technology for is inflatable habitats on surfaces like the moon,
There's
Mars.
no
things like
wind
that.
on the moon.
Yeah. Yeah. They would be easier, I think.
So not for Titan though.
Yeah, probably not great for Titan.
Well, you've always got that oxygen problem, right? Which we already said, like no breathing creature should go anywhere near Titan because they just light
Unless
on
you breathe
fire.
methane.
There is that.
Well, they just light on fire, right? You brought the oxidant to the party. So, Johnny J is asking in the comments, wouldn't a micrometeorite be lethal to inflatable habitat? No, these things are, they've thought of this. They're covered in like a Kevlar, very like a woven mesh. And so in many cases, they're actually very resistant to micrometeorite impacts, much more so than the ones that, the tin can ones. And even if they do, they don't necessarily explode. They don't decompress explosively because they've got a lot of sort of strength, and so they will just leak, and they'll be able to fix it, and it's a fairly easy fix. So this is the big concern.
Says the person comfortably in his house on
Yeah,
Earth.
here I am, never to go to space. Fairly easy to fix.
Ah, it's an easy
Never
fix.
say
You're
never.
leaking air.
Yeah.
So never say never. 2024 is not that far away, as you said.
And one of the things that's also quite interesting is that if you go back to the original von Braun plans to send humans to Mars, he was thinking inflatable habitats would be the way to go, and so it's sort of full circle. So I think inflatable habitats will play a role in future space exploration and room for people in space. It gives you a lot of room. Imagine this gigantic volume of space that you could float around inside. That would be so much fun. I'd do
Bounce
it.
house in space.
Bouncy castle.
Bouncy castle in space.
Bouncy space.
Yeah, it would be.
Bouncy space
It
castle.
would be a bouncy space
The
castle.
Bigelow Bouncy Space Castle.
Ooh, new branding.
BSG. There you go. BSC. All right. Well, let's wrap things up then. And so we're gonna test out new ways to close this show. And today, I would like to know what you guys are watching right now. So, Paul, what are you watching, reading, playing? How do you, when you're not creating media, how are you entertaining yourself?
There is time between. Well, actually, honestly, I would love to be digging into a book or a TV show, but I'm writing a book right now. And that's taking up like every ounce of free time. I know you don't measure free time in ounces, you typically, but I do. And it's consuming all of it.
Let's help you plug your book. What are you writing about?
Yeah.
I'm right. It's called The Universe Doesn't Care About You, and it's way bigger and messier than you think. Will be published by Prometheus Books in fall or winter of 2018 in a bookstore and online retailer near you. First, I have to write it.
Have you ever written a book before?
I've never written a book before, and now I know why.
I will never write a book again.
I wrote a thesis. That's a book.
Yeah, I wrote a thesis. That was great. This is big, and it's actually really fun, really challenging. But it is my life right now for the next 6 months.
Morgan, what are you reading, watching?
Yeah, I have not been writing a book, but I have been reading a book about how to make cocktails, cleverly entitled The Bar Book by Jeffrey Morgenthaler. And I'd like to say I know a lot about making cocktails now, but I'm like 50 pages in, and all I've learned about so far is fruit. It's, how do you juice a fruit? How do you squeeze a fruit? How do you puree a fruit? I didn't even know there were so many fruits in the world. But if you want a book about making cocktails that has at least 50 pages about the art of refrigerating a fruit, then the bar book by Jeffrey Morgenthaler is the one to get.
That's awesome. Kimberly, what are you doing with your spare time?
So with my spare time, I guess I'm catching up on really old TV shows, which is not the interesting part. But I have been listening also a lot to the Hamilton soundtrack, which is one of my new favorites. I'm doing my darndest to actually memorize all of the words, which is much harder than for any other musical. There are so many words in that show. But why? Are there words, or why do I like it?
Why are you memorizing it?
It's one of those things that I sort of have to do with musicals because I like singing along to them. Because I perform in musicals, and so
You
it's
wanna
sort
sing
of
one
habit
for
to
us?
sing it. Oh, not right now, no.
Well, I know what your topic will be next week.
Next week
Oh gosh.
Bring it.
You have to give me like at least 10 minutes
to warm up.
to remember what musicals. Anyway, I've been listening to Hamilton pretty much nonstop, and I'm really excited because it's coming to DC in a couple months from now, and so I'm crossing my fingers for tickets.
So
Good luck.
That are not going to cost me an arm and a leg.
I have been watching Harmon Quest, which is a animated version of Dungeons and Dragons, or actually Pathfinder, played by Dan Harmon and friends with very special guest stars every week. And I've been playing role-playing games for most of my life. That's the books that I wrote. You can see them right there. But it's such a great idea to see someone's role-playing games turned into like animated, because the things that happen in these stories are so weird that it's just great to see them turn into animation. And they're all so funny, and it's great. So I really, really am enjoying that. They're into season 2 now, and it's a lot of fun. So if you like Rick and Morty, the minds behind Rick and Morty, I think you'll enjoy Harmon Quest.
Nice.
Right on. Okay, well, that's it. Time to wrap things up. So you know where to find us all. So I'm just going to say thanks to my co-host this week. Thanks, as always, to the WSH crew for being the heart and soul behind what we do here. Go to wshcrew.space and join up. If you're watching this live, don't forget we do this as a podcast, so you can listen to it in your ear holes as opposed to
Rate us on
having to watch it.
iTunes.
Rate us on iTunes. Yeah, definitely.
Yeah.
And then this was our shot at having a different close to the end of the show.
How'd that work out?
How did that work out for you? Yeah. If you liked it, good. If you didn't like it, too bad. You didn't suggest a better closing.
Fair enough. Touche.
That's a hint to suggest something better for us to talk about at the end.
We just leave. How about we just
believe? All right.
Just done. Just the audio cuts out.
That's it. This is over.
Yeah.
All right. I'm going to put you all on the screen. There they all are.
Brady Bunch Wave.
Brady Bunch Wave. Thanks, everyone.
I'm sad.
Bye.